Shit. Get out with LPP. Yeah, you know me. Get out with LPP. Yeah, you know me. Get out with LPP. Yeah, you know me. Who's down with LPP? Every last on me. Get out with LPP. Yeah, you know me. Get out with LPP. Yeah, you know me. Get out with LPP. Yeah, you know me. Who's down with LPP? What a late.
Alright, welcome to section 5.1. We're going to be talking about polynomials this entire unit, how we can kind of add them, subtract them, multiply them, divide them, factor them, how we can graph them. So a big unit on polynomials, but we're going to start off just talking about operations with polynomials, specifically how we can add, subtract, multiply, and factor polynomials. So we're going to have a little bit of a review of factoring. But in order to do anything with polynomials, we need to understand what a polynomial is. And a polynomial is one or more monomials, okay, monomials just meaning terms, put together by addition or subtraction. So here's a little example. Notice how we have 4 terms, 4 monomials, and we just put them together by either adding or subtracting the terms. Now what's special about a polynomial is that each exponent must be a whole number, meaning a 3, in this case a 1, in this case a 5. So we can't have any fractions, we can't have any decimals. Okay, we're specifically looking at positive whole numbers as our exponents. But the coefficients, on the other hand, can just be any real number. So it could be a -2 or a +8 or maybe 2.5 or even a fraction. So we really don't have any restrictions on what the coefficients could be, but our exponents have to be positive whole numbers. So in terms of a polynomial, we can, once we have one, we can classify 3 different things within this polynomial, either the constant term, the degree, and the leading coefficient. So in our example, the constant term is the only term without a variable, meaning that it's essentially constant. It's not going to change. So if you look at our polynomial, the only one without a variable is our +1 on the end. So in this case, this is our constant term. Now it could depend on your polynomial. Maybe it's 50, maybe it's -2, but it's just the term, the constant, without a variable. Now the degree, on the other hand, is the largest exponent kind of in your polynomial. If we look at our largest exponent, it looks like that would be a 5. So the degree of this polynomial would be a 5th degree. And the leading coefficient is the coefficient of the degree term. So if this is my degree, the coefficient is the number out front, which looks like a -3. So once we have a polynomial, we can find those 3 different things. What else we can do with a polynomial is put it into what's called standard form. And this is where we write the degree term first. So in other words, we would write -3x to the 5th first. And then all of our other terms kind of go in successive order in a decreasing fashion. So if we start with -3x to the 5th, the next largest degree we would have is 3. That's what we would have left. So we would write -2x to the 3rd, and then the next highest degree we would have is a 1. So we would have an 8x to the 1st, but you don't have to write it, which means our constant term is always going to come last because it doesn't have a degree, it doesn't have a variable with it. So what we can do is, normally you're going to see all of these polynomials written in standard form where our exponents kind of decrease in this fashion as we go off in our equation. So standard form, really big idea. This is how we're going to see all of our polynomials, or at least this is how we want to write all of our polynomials. So now that we know what a polynomial is, we can talk about adding, subtracting, and multiplying them together. Notice how we're taking our first polynomial in parentheses and we're adding the second one. What's nice about addition is that we essentially have these positive ones in front of our parentheses, in front of our polynomials. And if we want to add them together, we first need to distribute in the ones. But when we distribute in a 1, that really doesn't change anything because we're just multiplying by 1. And that doesn't do anything. So we can just think about dropping the parentheses because nothing's going to change when we bring in those positive ones. So now that the parentheses are gone, we can combine some like terms. Looks like 6a to the 3rd and another 6a to the 3rd is going to give us 12a to the 3rd. We have a 5a and a 1a, which would give us 6a. And then our constant of -2 on the end. So there's our standard form polynomial after we add those together. Now, subtraction, on the other hand, is a little bit trickier because we still have those ones out front, but we got to be careful because notice how in our first distribution, nothing really changes because it's a positive 1. But our second distribution will change because we're essentially distributing in a negative 1 since we're subtracting. So we got to be careful with subtraction because all of these signs are going to change once we bring in that, that should be a minus. Once we bring in that negative 1. And I almost fell victim right there, but I caught myself. So all the signs change. Now that we distributed in the 1s, let's combine some like terms. Looks like we have a 4x to the 4th and a negative 1x to the 4th. So that would give us 3x to the 4th. Our x squared term doesn't have anything else to match with, so we'll leave that go. And then our constant terms 2 and 7 looks like we're going to have a 9. So there's our standard form polynomial after we subtract our original polynomials. Now, in terms of multiplying, some of you may have heard of FOIL before, but that's only in the case when we're multiplying a polynomial of 2 terms with another polynomial of 2 terms, because we have that first, outside, inside, last. I prefer to call multiplying polynomials double distribution, or at least in this case, it's double distribution, because we need to distribute in the 7n to everything, but we also need to distribute in the 1 to everything. So we have this double distribution happening when we multiply this particular polynomial. So if we check it out, we have 7n times n squared, which is 7n to the 3rd, and then 7n times 6n is 42n squared, and then 7n times 3, we get 21n. So that's our first distribution, but then we got to distribute in a 1, so I'm left with n squared plus 6n plus 3. So now that all of our parentheses are gone, let's combine some like terms. I only have a 7n to the 3rd because there are no other n third terms left. I do have a 42n squared and a 1n squared, so that would give us 43n squared. Next we have 21n and 6n, so that gives us 27n. And our last constant is just a 3. So there's our standard form polynomial once we're done multiplying. Alright, so now that we added, subtracted, and multiplied some polynomials, we're going to take a look at factoring again, how we can factor some polynomials. Minor review of what we've been doing so far this year, but we are going to throw in maybe some ones you've never seen before. I don't know if you've seen factor by grouping. It's not that bad, it's just a different type of factoring. But we're going to start things off with differences of squares. Now, particularly we want to be sure we know what the word difference means, because that's a really big idea in difference of squares. Difference just means subtraction. So we want to find 2 perfect squares. Okay, a squared and b squared are perfect squares, and notice how we are subtracting them. So if this is the case, we can factor it in this specific fashion where we take the perfect squares a and b, and we use conjugates to find our factors. One's positive and one's negative. That's the idea of a conjugate. Okay, a conjugate is, notice how we're using the same terms a and b, but the 2 factors just differ in operation. One's being subtracted and one's being added. Okay, that's the idea of a conjugate. We're going to use these later this year, so I thought I'd just throw in the word now. But a conjugate, notice how the terms or factors are the same. One's just being added and one's just being subtracted. So let's take a look at our first example. We want to use difference of squares, but before we try to find the perfect squares, let's try to factor out something first. That's normally going to help us. Notice how both of these terms have a t in common, so we can initially take out a t just to simplify it a little bit further. So if we take out a t, we're left with t to the 4th minus 16. And notice how this leftover piece is a difference of squares. T to the 4th is a perfect square, 16 is a perfect square, and notice how we are subtracting it. So we can factor this piece further into the 2 conjugate pieces. The perfect square of t to the 4th is t squared. Notice how we're just taking the 4th and evenly dividing it between the 2 factors, so 2 of the 4 t's go here and the other 2 go here. The perfect square of 16 is 4, started as a 4, because 4 times 4 gives us 16. And to use the idea of a conjugate, we need one that's minus and one that's plus. So that's not too bad, but notice how we can still factor, okay? This group right here, the t squared minus 4, is another difference of squares. T squared can be broken up into t and t, and 4 is a perfect square. It started as a 2, so we can still factor further. So I have the t. This group is going to factor further. But our second one is not, because notice how it's not a difference of perfect squares. Okay, we are adding. Difference of perfect squares means that we need to be subtracting. So to factor this piece further, t squared can be broken into a t and a t. 4 can be broken into a 2 and a 2, because those are the perfect squares. And to use the idea of a conjugate, one's plus and one's minus. So that's as far as we can factor this particular polynomial using the difference of squares to help us with that. So what I want you to do is pause the video and try number 5 on your own. Alright, if we check it out, 81's a perfect square. It started as a 9, so we can use 9 and 9. X squared's a perfect square. It started as an x and an x. 100 is a perfect square. It started as a 10 and a 10. And then y to the 8th is a perfect square. If we divide by 2, we're going to have a y to the 4th and a y to the 4th. Since they're conjugates, one's minus, one's plus. But this one can't be taken any further because 9 is a perfect square, but notice how 10 is not. So this is the only one we could possibly take further because it's a subtraction, it's a difference, but since they're both not perfect squares, we can't go any further. So that's as far as we can go for number 5. Alright, so moving on to factor by grouping. Maybe this is kind of new to us, maybe it's not. But the whole idea with factor by grouping is to look for 4 terms. So notice how we have 4 terms in this polynomial, and we have 4 terms in this polynomial. That's kind of a hint that we want to try to do factor by grouping. So how factor by grouping works is literally we're going to group terms together. Specifically, we're going to group the first 2 terms together and the last 2 terms. Okay, so we're going to group those together. Now what we want to do is just focus on our first group. What can we factor out of 56v to the 3rd minus 49v squared? Well, 56 and 49 both have a 7 in common, and v cubed and v squared both have 2 v's in common. So overall, from our first group, we can take out a 7v squared. Now if we take that out, what we're left with is an 8v minus 7. So that's what our first group is telling us. Now if we take a look at our second group, what can we take out of that one? This one has a 48v minus 42. Well, 48v and 42 both have a 6 in common, so we're going to take out a positive 6. And when we do that, we're left with 8v minus 7. And look at that. Okay, what this leftover quantity here and this leftover quantity here actually match, and that's good because we want that to happen. Okay, so the reason we want that to happen is because this matching group is one of our factors. Okay, so it came up from our first group and it came up from our second group, so it's an overall factor of this original polynomial. So since they match, that's one of our factors, and the other factor happens to be the 2 pieces that we initially removed. So our second factor would be a 7v squared and also a positive 6. So our first factor are the items that match. Okay, we absolutely want them to match. And the second factor are the terms that we initially factored out of our 2 groups. What I want you to do is try to pause the video and try this one on your own. Try number 7. Alright, so let's check it out and see how we did. Group our first 2 terms together and our last 2 terms. Don't forget to group the minus sign because it's attached to that 36. Okay, it's actually a negative 36xd squared c. So our first group, we can factor out a 21a squared d squared, and we're left with 2c plus 7d. Now we want to be strategic on what we take out or factor out from our second group because we know we want to match this leftover quantity. So in order to match it, we have to remove or factor out a negative 18 xd squared. So when we take out the negatives, notice how that's going to change both of these to positives, which is what we want because we want a positive 2c and a positive 7d. So factoring out a negative might be a key instance in order to get these 2 factors to match. So since they match, okay, that is going to be one of our factors. And the other factor are the quantities that we initially factored out. So we have a 21a squared d squared, and then we also factored out a negative 18x d squared there. Hopefully we did really well with that one. Alright, so let's take a look at an example of a quadratic. These have the form of ax squared plus bx plus c, and we've been doing these so far this year, so let's just kind of take a second to review. Let's first try to take something out. Is there anything that all three of these have in common? Well, it looks like 9, 66, and 105 are all divisible by 3. So I'm initially going to take out or factor out a 3 from everything, so I'm left with a 3r squared minus 22r plus 35. Now this is tricky because remember, if it looks like ax squared, we want this a to essentially be 1. That way we can just think about what multiplies to c and what adds to b. But notice how our a is not a value of 1. Okay, so if we were to label this as a, b, and c, we can clearly see that. So in order to factor further, if we remember from the beginning of the year, we need to actually find the a times c value. 3 times 35 is 105, and our b value is negative 22. So we don't want to think about two numbers that multiply to 35 but add to a negative 2. We actually want to think of two numbers that multiply to a 105 and add to a negative 22. So if we think about those numbers, what multiplies to 105 but adds to a negative 22, I think that's going to be a negative 15 and a negative 7. Okay, so this group right here, this quadratic, factors further to these two separate factors. Notice how I still wrote my value of 3 out front because I initially took that out. But since we had an a value of 3, this is where we need to divide both of those numbers we found by 3 in order to go a little further. So notice how this fraction will simplify nicely to a negative 5, but this 7 over 3 does not, so we move the 3 to the coefficient in front of the r. Alright, so there's as far as we can factor that quadratic. Moving on to our last type of factoring, we have the quadratic form, which kind of looks similar to this, but notice how our degree in this case is actually 4 and it's not 2. Okay, so the degree in these quadratic form ones are something other than 2, but what's nice about these is that they act very similarly to the ones that we just did up here. So we still want to try to figure out, is there anything we can initially remove? It looks like our coefficients all have a factor of negative 3. Okay, I'm going to deal with a positive first term, so I'm going to take out a negative 3. So I'm left with an x to the 4th minus 8x squared minus 9. And notice how this kind of looks like what we had here, but it's nice because our first coefficient is a 1. So we can simply try to figure out what multiplies to negative 9 but adds to a negative 8. We don't have to do any of this a times c business or divide by that a term because our a term is 1. It's nice and simple. So two numbers that multiply to negative 9 but add to a negative 8 are negative 9 and a positive 1. Now what's different about this is that we're starting with an x to the 4th. Okay, we're not starting in this case with an r squared. But notice how if we had an r squared, we put one r here and the other one here. It's like we evenly divided it, like we talked about kind of in that difference of square section. So if we're starting with an x to the 4th, we want to evenly divide it between our two factors. That means I would need 2 x's here, an x squared, as well as 2 x's here. So that's what's different about the quadratic form. Since we're dealing with a different power, we need to evenly divide it between the two factors. Now we got to be careful because notice how this factor is a difference of squares. X squared is a perfect square and so is 9. So this factor can be taken further. Let's think about it. Our last one can't be because it's not a difference. It is a sum of squares. It's not a difference. The perfect square of x squared is x, and the perfect square of 9 is 3. Again, if we started with 2 x's, notice how we evenly divided the 2 between the two factors. And these must be conjugates, so one's going to be positive and one's going to be negative. So that's as far as we can go. That's as far as we can factor for this example. Go ahead and try number 10. This one's tricky, but I'll be back in a little bit to see how you do. Alright, so this one can be kind of tricky. Notice how we have three terms, just like we had three terms here, as well as three terms here. So we want to try to think about two numbers that multiply and add, and specifically to negative 15 and negative 2, because our first term is a 1. Okay, again, we don't have to do any of this first term times last term business, because our first term is a 1, nice and simple. So two numbers that multiply to a negative 15, but add to a negative 2, are negative 5 and a positive 3. Okay, so those are nice and easy. But since I'm starting with an a to the fourth, I need to evenly place that within our factors. So we would have an a squared and an a squared. But I'm also starting with a b to the fourth on the end, so I evenly need to divide this b to the fourth into our two factors, which would be a b squared and a b squared as well. Now again, if you're not quite sure, you can always distribute to check your work. If we were to take a squared times a squared, that would give us a to the fourth. A squared times 3b squared would be 3a squared b squared. Negative 5b squared times a squared is negative 5b squared a squared. And then negative 5b squared times 3b squared is a negative 15b to the fourth. So notice how we have like terms in the middle. Both these have a squareds, b squareds in them. So that would give us a negative 2a squared b squared. And we're left with the negative 15 b to the fourth on the end. So notice how when we check our work, when we actually go through and FOIL or distribute, we get originally what we started with. So you can always check your work when you're factoring. You can always distribute to see if you get what you originally started with. Alright, so since we're talking about factoring, the zero product property, what I call ZPP for short, is very related to how we can solve these polynomials once we factor them. So I just want to know, are you down with ZPP? So what the zero product property, or ZPP, tells us is that if we were to take two things, two numbers or two terms, in this case a times b, and we get an answer of 0, like we for sure know that our answer is 0, then either a has to equal 0 or b has to equal 0. So if a is 0, it doesn't matter what b is, because 0 times b is just going to be 0. And if b is 0, it doesn't matter what a is, because a times 0 is just going to be 0. So if our equation specifically equals 0, we know that one of the two parts in this case has to be 0 itself. We've been using this idea this year, this ZPP, to help us solve polynomials after we actually factor them when we know they equal 0. So for example, we've been doing this year, either the 3x equals 0, that's kind of our first part, or the 2x minus 8 equals 0, that would be our second part, or even, oh wait, that should be 4, 4x plus 5 equals 0, that would be our third part. So if we solve for x, by dividing by 3 in this case, our x solution would just be 0. If we added 8 and divided by 2, our x solution would just be 4. And over here, another x solution would be, if we were to subtract 5 and divide by 4, we would get negative 5 over 4. So factoring helps us break down the polynomial, but since we can set it equal to 0, that will help us find our solutions for x. So let's try to use our ZPP product property and factoring to solve all of our solutions in this case. So taking a look at what we have here, let's always try to take out a common term before we start anything. So taking a look at what we have here, it looks like they all have at least two x's in common. So let's take out two x's. So I'm left with x to the third minus x squared plus 3x minus 3, and all of that equals 0. So that's all nice. We have one piece that's showing up here, just kind of like the 3x was shown up here, but we want to try to factor as much as possible. So take a look at what we have left inside the parentheses. We have 4 terms, which means we could probably do factor by grouping. So if we take a look at our first 2 terms and our last 2 terms, let's see what we can get. Alright, so I'm not going to forget about this x squared. I'm going to put a little star there so I remember, but I'm only going to focus on this inside a leftover quantity. So out of my first group, looks like we can take out two x's, and I'm left with an x minus 1. Out of my third group, it looks like I can take out a positive 3, and I'm left with an x minus 1 as well, which is good because when we do by grouping, we want these to match. So our two factors would be an x minus 1, and then the x squared plus 3. So this is how our leftover quantity factors. So overall, I'm left with the x squared I initially took out, and then the inside factored as x minus 1 and x squared plus 3. Now, since all of this equals 0, we can break it apart into the little pieces to find our solutions for x. So either x squared equals 0 from our first piece, or x minus 1 equals 0 from our second piece, or x squared plus 3 equals 0 from our third piece. Okay, we can't take this one any further because notice how it's not a difference of squares, we're actually adding, so we can't go any further with this piece. Now, in our first possible solution, we could square root both sides to get rid of the squared, which means x would equal the square root of 0, which is just 0. So there's one possible solution. Our second piece, when we add 1 over, we get an x solution of 1. And if we look at our third piece, we can subtract 3, which would give us x squared equals negative 3. And when we square root both sides to get rid of that power of 2, we're going to be left with an imaginary number because we're dealing with the square root of a negative number. So the negative changes to an I, but the square root of 3 does not simplify, so we leave that the same. Okay, square root of 3 can just stay. But also we got to be careful because since we took the square root of both sides, we need a plus and a minus answer. Okay, we actually get two answers in that case. So even though this is a negative solution and a positive solution, okay, we get two solutions, and even also though it's an imaginary solution, it's still a solution by factoring. Okay, we want to find all solutions, even if they're real numbers or even if they're imaginary. Alright, so let's take a look at our last one. This one can be tricky because we kind of have terms all over the place, but remember, we want our equation set equal to 0. That way we can use our ZPP. Alright, so in order to get it set equal to 0, let's subtract our 7x squared over here. And notice how I'm putting it kind of in between the x to the third and x and the regular x because it would be found in between those two exponents. So we're left with 0, and we have 5x to the third minus 7x squared plus 6x. Now since it's equal to 0, we want to try to factor it. That way we can use our zero product property to find our solutions. So taking a look at it initially, it looks like I can factor out an x because they all have an x in common. So I'm left with 5x squared minus 7x plus 6, and that equals 0. Now I want to try to factor as much as possible. So looking at these three terms in here, notice how our first term, if we were to label it A, B, and C, is not 1. So I have to go through that process of trying to find A times C, which would be 30 in this case. 5 times 6 is 30. And then our B value would be negative 7. So if we try to think about two numbers that multiply to 30, but add to a negative 7, well, if we were to list the factors of 30, we would have 1 in 30, 2 in 15, 3 in 10, and 5 and 6. But notice how none of those different combinations can actually get us here to a negative 7. It kind of looks like 3 and 10 would, but notice how the 10 would actually have to be negative, and if we were to do 3 times negative 10, that would give us a negative 30, and we don't want a negative 30, we want a positive 30. So since none of these factors of 30 are able to be added to a negative 7, that means we cannot factor this any further, alright? So we tried that process, it's not working, but that's okay, because when we cannot factor something, we can use the handy-dandy quadratic formula to help us out. So even though we tried factoring, let's try to use our quadratic formula. So specifically in this case, 5x squared minus 7x plus 6, we already labeled A, B, and C, which is going to help us try to fill in these different coefficients here for A, B, and C. So our solutions from this case are coming from the quadratic formula, but our solution for this x variable out here would just be x equals 0, because either our first piece equals 0, like we can state here, or our second piece equals 0, and that's what we're going to find over here using our quadratic formula. Notice how we're actually solving for x. So if we use our quadratic formula, the opposite of b, or in other words, the opposite of a negative 7 would be a positive 7. And underneath our square root, we want b squared, so negative 7 squared, minus 4 times a, which was 5, times c, which was 6, and all of that is over 2a, which we labeled as 5. So x equals, we have 7 plus or minus. Now, we have negative 7 squared minus 4 times 5 times 6. If we try to do all of that in our heads, maybe on our calculator, I believe we get a negative 71, and that's all over 5 times 2, which would give us 10. Now we can keep going because we can simplify this radical even though it's negative. That means we're going to have an imaginary I from that little negative piece, but the square root of 71 cannot be simplified any further, so we're just going to leave it the square root of 71. Now it's all over 10, so there is our other solutions for x. We'd have a positive, or in other words 7 plus I squared of 71 over 10, or we could have the negative. Now something else you can do if you wanted to actually write this different was to write it as 7 over 10 plus or minus I square root of 71 over 10 as well. Okay, that's just a different way of writing it. Notice how both of these pieces are being divided by 10. So if they're both being divided, that means we can divide kind of each one separately. So either one of these cases, they both mean the same thing. You're good to go. So your quadratic formula is going to be your handy dandy buddy whenever you cannot factor any further in order to help you solve for your x solutions. Alright, so I think that's it. Good luck on the practice and the application and that mastery check, and I'll see you guys later.